Right now, the planet most similar to Earth in the entire solar system is a world where the ground is hotter than an oven running at full blast for 4.5 billion years, where the air is 93 times heavier than anything you have ever breathed, where clouds made of sulfuric acid drift through skies that have never seen rain. This is Venus. It is nearly the same size as Earth. It formed from the same material at the same time, in the same neighborhood. There is serious scientific evidence that it once had oceans, and scientists now believe it may still have active volcanoes erupting today. Somewhere inside the most hostile world we know, there is a planet that could have been ours. If this video sparked even one new thought about the universe, a like costs nothing but helps everything for a small team trying to reach more curious minds. In 3, 2, 1, liftoff. There is a planet in our solar system that is so close to Earth in size, mass, composition, and orbital position that planetary scientists have spent decades struggling to explain how two worlds so physically similar could possibly have ended up so different. That planet is Venus, and the more carefully we study it, the more deeply unsettling the answer becomes. Not because Venus is alien, but because Venus is familiar, disturbingly, hauntingly familiar, like standing in front of a mirror that shows you a version of your own face, aged by something that should not have been allowed to happen. Let us begin with the numbers, because the numbers are the argument. Venus has a diameter of approximately 12,100 kilometers. Earth's diameter is approximately 12,700 kilometers. That is a difference of less than 5%. If you placed the two planets side by side at the same scale and looked at them from a moderate distance, you would need a measuring instrument to tell them apart. They are not similar in the loose, approximate way that people sometimes use the word similar when they mean roughly the same general category. They are specifically, quantifiably, almost precisely the same size. Venus has a mass approximately 81% of Earth's. It has a bulk density of approximately 5.24 grams per cubic centimeter, compared to Earth's 5.51. That density similarity is not a trivial fact. Density tells you what a planet is made of at a deep level. Both planets have bulk densities that place them firmly in the iron and rock category, dense metallic cores surrounded by silicate mantles, topped by thin rocky crusts. Both worlds formed from the condensation of similar solid materials in the same rotating disk of gas and dust that surrounded the young sun approximately 4.5 billion years ago. Both planets were assembled from essentially the same raw ingredients in the same cosmic formation zone during the same geological moment in the early history of the solar system. Venus orbits the Sun at approximately 108 million kilometers. Earth orbits at approximately 150 million. In the vast spatial context of the solar system, which extends billions of kilometers from the Sun out to the distant regions where the outer planets move, that separation between the two planets is genuinely small. The gap between Venus and Earth is roughly 42 million kilometers, less than a third of Earth's orbital distance from the Sun. These two worlds are, in cosmic terms, nearly standing on the same street corner, and they formed from the same paving stones. Given all of this, the nearly identical sizes, the nearly identical densities, the nearly identical compositions, the neighboring orbital positions, the expected outcome Looking at the two planets 4.5 billion years ago from some distant vantage point would have been straightforward. Two rocky worlds with similar building blocks and similar gravitational situations should evolve along broadly similar lines. Both would outgas primitive atmospheres from volcanic activity. Both would receive sunlight, warm their surfaces, and radiate heat back to space. Both would settle into equilibrium states determined by the balance between incoming solar energy and outgoing thermal radiation, modified by whatever greenhouse effect their atmospheres created. The reasonable expectation was two habitable worlds. Instead, one of them is Earth, and the other is the most hostile planetary surface in the inner solar system. The surface temperature of Venus averages approximately 465 degrees Celsius, hot enough to melt lead, zinc, and tin simultaneously, hot enough to soften certain aluminum alloys, far above the boiling point of water at any pressure. The atmospheric pressure at the surface is approximately 93 times Earth's at sea level, equivalent to what you would experience diving approximately 900 meters below the ocean's surface. The atmosphere is 96% carbon dioxide. The clouds that cover Venus from pole to pole without a single break, making the planet the brightest object in Earth's night sky after the moon, are not made of water vapor. They are made of concentrated sulfuric acid, forming a corrosive, opaque layer between approximately 50 and 70 kilometers altitude that blocks all view of the surface in ordinary visible light and destroys any probe or instrument that is not specifically hardened to survive it. Below those clouds, no rain falls, no rivers flow, no ocean has existed on the surface in any condition we can currently detect. And yet, the chemical story embedded in Venus's own atmosphere contradicts the idea that this world was always this way. It is a story written in isotopes, in the relative abundance of two forms of the same element, and when you learn to read it, the planet looks completely different. Hydrogen has two stable isotopes. Ordinary hydrogen, the kind that makes up the vast majority of hydrogen in the universe, has a nucleus consisting of a single proton. Deuterium is a heavier form of hydrogen whose nucleus contains one proton and one neutron, making it approximately twice as massive as ordinary hydrogen. Both forms of hydrogen combine with oxygen to produce water, but they do not behave identically when it comes to escaping a planet's atmosphere. When hydrogen atoms are heated by solar radiation and solar wind in a planet's upper atmosphere and gain enough energy to escape the planet's gravity, the lighter ordinary hydrogen escapes more readily than the heavier deuterium. The difference in escape rates is real and predictable. So, over geological time, as a planet loses hydrogen to space, the ratio of deuterium to ordinary hydrogen in the remaining atmosphere climbs. The more water a planet has lost, the higher its deuterium to hydrogen ratio will be. The deuterium to hydrogen ratio in Venus's atmosphere, first measured by the Pioneer Venus spacecraft in 1978 and confirmed at approximately 120 times the terrestrial ratio by ground-based infrared observations in 1991, is enriched by a factor of roughly 100 compared to Earth's ocean water, a 100-fold enrichment. When the original Pioneer Venus paper was published in Science in May of 1982 under the title "Venus was wet," that isotope ratio was the evidence. It is not a model prediction. It is a direct atmospheric measurement, independently confirmed. It says, in the unambiguous language of chemistry, that Venus once had far more water than it has today, that the hydrogen from that water has been escaping to space over geological timescales, and that the current atmosphere carries the depleted, deuterium-enriched remnant of a much wetter past. How much water did Venus originally have? The pioneer Venus measurement established that at least 0.3% of a terrestrial ocean worth of water was outgassed on Venus. But that lower bound is almost certainly an underestimate of the original inventory, because it accounts only for what was outgassed late enough to leave a measurable signature in the current atmosphere. Models of planetary formation place Venus's original water endowment at potentially a significant fraction of Earth's, delivered by the same population of water-bearing asteroids and comets that supplied Earth during the period of heavy bombardment. The precise original quantity is not known, and is one of the central things the upcoming Da Vinci mission is designed to constrain. But the direction of the evidence is unambiguous. Venus once had water, probably a great deal of it, and almost all of it is gone. This means that early Venus billions of years ago, before the cascade that destroyed it had run its full course, was almost certainly not the scorched, bone-dry world that greets our spacecraft today. It was a planet with water on or near its surface, a planet where the chemistry that requires liquid water was at least possible, a planet that, by the most fundamental definition planetary scientists use, was potentially habitable. Now comes the question that defines modern Venus science, and that separates what we know from what we are still trying to understand. How long did that potential habitability last? In 2016, a team led by Michael Way at NASA's Goddard Institute for Space Studies published a three-dimensional climate simulation of Venus across its history. Using topographic data from the Magellan spacecraft, estimates of solar luminosity going back 4.5 billion years, and various assumptions about Venus's early ocean depth, atmospheric composition, and rotation state, the results were striking. Under many of the scenarios they modeled, early Venus, particularly a slowly rotating Venus, which through a mechanism involving dayside cloud formation reflected enough solar energy back to space to moderate surface temperatures, maintained conditions compatible with liquid water, not for a few 100 million years, but for as long as approximately 3 billion years. A follow-up paper in 2020 deepened those findings. The slow rotation of Venus, which today gives the planet a solar day of approximately 117 Earth days, would have caused long dayside heating that drove vigorous convection and built a thick, persistent cloud deck over the sunlit hemisphere. That cloud deck acted as a solar reflector, bouncing a large fraction of incoming sunlight back to space and preventing surface temperatures from rising uncontrollably. The very feature of Venus's rotation that seems unusual, its sluggishness, may have been what gave it its longest period of habitability. But those models sit in ongoing tension with other research. A 2023 paper in the Proceedings of the National Academy of Sciences examined a narrower range of possible early Venus scenarios, constrained by what oxygen loss and argon degassing can tell us about the planet's geological history, and concluded that Venus may have been uninhabitable for over 70% of its total age, roughly 3 billion years of hostility, with any habitable window confined to the earlier portion of the remaining time. A separate line of modeling incorporating the dynamics of Venus's early magma ocean phase has suggested that, for some initial conditions, surface water may never have condensed at all. The water may have remained as vapor in a dense steam atmosphere during the earliest epoch, then been lost to space before liquid oceans could form. The honest position, given this landscape of models and their conflicting conclusions, is that Venus's early habitability remains genuinely uncertain. What is not uncertain is the isotope signal in the atmosphere, which demands that some quantity of water was present and was lost. What is not uncertain is that the planet crossed into complete uninhabitability at some point, and that the crossing was permanent. What is not certain is exactly when the threshold was crossed, how much water existed before it was crossed, and how long, if at all, surface conditions were compatible with life as we understand it. This uncertainty is productive. It is not the uncertainty of ignorance, but of incomplete measurement, and incomplete measurement has a solution. That solution is sending instruments there. For now, consider what it means to hold both possibilities simultaneously. On one end of the range of models, Venus was habitable for billions of years, long enough for life to potentially have emerged, evolved, and established itself in ways that might have left some detectable signature. On the other end, Venus may never have had the extended, stable liquid water surface that life as we know it requires. Between these extremes lies a gradient of scenarios, each consistent with some set of observations and some set of assumptions, none of them definitively ruled out by current data. This is not a comfortable position for a scientific community that wants answers, but it is the actual state of knowledge. What is shared across all the scenarios, including the pessimistic ones, is the recognition that Venus and Earth started from the same conditions and diverged. The divergence was not the result of some obvious, dramatic difference in raw materials or position. It was the result of processes that operated on the two planets differently, producing outcomes that could not be more distinct. And the specific identity of those processes, the physical chain of events that sent Venus down the path it took, is one of the most important things in planetary science to understand, because every time we find an Earth-sized planet orbiting in the habitable zone of another star, we are implicitly asking, is this going to turn into an Earth, or is this going to turn into a Venus? There is one more thing about Venus that must be established before the transformation can be fully understood. It concerns not the planet's size or composition or orbital distance, but its rotation specifically, the extraordinary slowness and backward direction of that rotation, and the fact that this strange spin may be the key to the entire story. Venus rotates on its axis once every approximately 243 Earth days, the slowest rotation of any planet in the solar system. It rotates retrograde. If you were above Venus's north pole looking down, the planet would spin clockwise, the opposite direction from Earth and most other planets. The consequence of this retrograde rotation is that on Venus, the sun rises in the west and sets in the east. A Venusian solar day, the time from one sunrise to the next, is approximately 117 Earth days. The planet's year, the time it takes to orbit the sun, is approximately 225 Earth days. So, on Venus, a day is shorter than a year. A resident of Venus, if such a thing were possible, would experience the sun crossing the sky from west to east over the course of about 117 days, then darkness for another 117 days, with the sun rising in the west again. No one is certain how Venus came to rotate this way. The leading hypothesis involves a large impact in the planet's early history that dramatically altered its rotation, combined with atmospheric tidal forces, the gravitational pull of the sun on the dense Venusian atmosphere that over billions of years further modified the spin. Whatever the cause, the current rotation state is a fundamental feature of the planet that shapes everything else about its climate, its atmospheric dynamics, and potentially its habitability history. Because here is what that slow rotation means for early Venus in the context of Michael Way's models. a slowly rotating planet, accumulates solar heat on its day side for an extraordinarily long time before the rotation carries that face into shadow. On a quickly rotating planet like Earth, a given patch of surface spends roughly 12 hours in sunlight and 12 hours in darkness, and the temperature swings are moderated by that alternation. On a slowly rotating planet like Venus, a given point on the surface bakes in direct sunlight for weeks at a time in the current state, for over 50 consecutive Earth days before the rotation carries it away from the sun. That extended dayside heating drives intense convection in the atmosphere. Warm air rises dramatically over the sunlit hemisphere, pulls cooler air in from the night side, and creates a circulation pattern that, with liquid water present to evaporate and condense, produces thick, persistent clouds on the day side. Thick clouds mean high reflectivity. High reflectivity means a large fraction of incoming solar energy bounces back to space before warming the surface. The slow rotation, paradoxically, may have given early Venus a higher albedo than Earth, a better insulated planet, kept cooler by its own clouds, despite being closer to the sun. This is the kind of counterintuitive physical chain that makes planetary science difficult and fascinating simultaneously. The feature of Venus that looks most exotic and most different from Earth, its bizarre, ultra-slow backward spin, may have been precisely the feature that kept it habitable for as long as it was. And the loss of that protective cloud deck, as the planet warmed and the water supply that fed those clouds began to dwindle, may have been the moment when the last defense against the runaway greenhouse fell away. The surface that early Venus kept sheltered beneath those clouds was a rocky, volcanically active landscape shaped by internal heat and geological forces that are still operating today. It was a surface that received water from the same sources as Earth, cometry, and asteroidal delivery, and that had liquid water interact with its rocks in ways that may have, for a time, created the conditions for weathering, for chemical cycling, for the early steps of the kind of geochemistry that, on Earth, preceded and enabled the emergence of life. And then the sun kept brightening, and the water kept warming, and something changed. Something in the balance of incoming energy and outgoing radiation, something in the feedback loop between surface temperature and atmospheric water vapor that started a chain of events with no end state except catastrophe. That chain of events, in every mechanistic detail the science can currently support, is where this story goes next. Everything that happened to Venus began with an energy imbalance, not a dramatic one, not a sudden one, but a structural one, a difference built into the geometry of the solar system that the planet had no mechanism to overcome once the conditions were right for it to matter. Venus orbits at approximately 108 million kilometers from the Sun. Earth orbits at approximately 150 million. That difference means that every square meter of Venus's upper atmosphere intercepts approximately 2,600 watts of solar energy, compared to Earth's approximately 1,360 watts per square meter, twice the incoming power. And while each planet reflects a portion of that incoming energy back to space, Venus, with its highly reflective cloud deck, actually reflects considerably more than Earth does. In absolute percentage terms, the raw difference in incoming energy creates a thermal gradient between the two worlds that their respective atmospheres must work to manage. Earth manages it through several interlocking systems, the most important of which we will examine in close detail. Venus, for reasons that are either structural or that developed from an early tipping point, lost the ability to manage it. And what happened afterward was not a gradual, steady warming, but a self-amplifying cascade in which each change made the next change more likely and more severe. To understand the cascade, you need to understand a physical concept that sounds simple but is not: the atmospheric feedback loop. In a feedback loop, a change in some system produces an effect that either counteracts the original change, stabilizing the system, or amplifies it, pushing the system further in the same direction. The first type is a negative feedback stabilizing. The second type is a positive feedback destabilizing. Earth's climate is full of both kinds. On Venus, a specific positive feedback loop overwhelmed whatever negative feedbacks were operating, and once it did, the result was irreversible. The feedback loop that destroyed Venus is driven by water vapor. Here is how it works, step by step, at the level of physical mechanism rather than metaphor. The surface of early Venus warmed either from the brightening sun, from changes in its volcanic outgassing rate, or from some combination of the two. A warmer surface causes liquid water, whether in oceans, lakes, or surface reservoirs, to evaporate more rapidly. Water molecules leave the liquid and enter the atmosphere as vapor. Water vapor is an extraordinarily effective greenhouse gas. On Earth today, water vapor accounts for roughly half of the total natural greenhouse warming, more than carbon dioxide. This is because water molecules absorb infrared radiation across a broad range of wavelengths, trapping heat that would otherwise escape to space through the top of the atmosphere. So, more water vapor in the atmosphere means more infrared radiation absorbed, which means more heat retained, which means a higher surface temperature. A higher surface temperature means faster evaporation. Faster evaporation means more water vapor in the atmosphere. More water vapor means more heat retained. The loop closes, and each iteration pushes the system to a higher temperature and a higher atmospheric water vapor content than the previous one. The positive feedback is engaged. On Earth, this feedback loop is real, but it is constrained. The tropopause, the cold boundary between the lower atmosphere and the stratosphere, sitting approximately 10 to 15 kilometers altitude, acts as a cold trap for water vapor. As air rises through the troposphere, it cools. Water vapor condenses and falls back as rain long before it can reach the stratosphere. The result is that water vapor is largely confined to the lower atmosphere, where its greenhouse effect operates, but where it is continuously cycled back to the surface as precipitation. The amount of water vapor in Earth's atmosphere cannot grow without limit because the cold trap prevents it. The feedback loop is real, but it is throttled. On a Venus that was warming enough to push surface temperatures above the point where the cold trap could function effectively, where the atmosphere became too warm throughout its depth for water to condense out before reaching high enough altitudes to be photolyzed by ultraviolet radiation, the throttle was lost. Water vapor could rise high enough in the atmosphere to be broken apart by ultraviolet photons from the sun, and that is where the second destructive mechanism engaged. Ultraviolet radiation carries enough energy per photon to break the chemical bonds that hold water molecules together. When a UV photon strikes a water molecule in the upper atmosphere, it can split it into its components: 2 hydrogen atoms and 1 oxygen atom. This process is called photolysis, and it happens on Earth too, in a thin layer high in the stratosphere. But on Earth, there is so little water vapor in the stratosphere because the cold trap has removed it from the atmosphere well below that. Photolysis destroys only tiny amounts of water. On a Venus that had lost its cold trap, with water vapor rising freely into the upper atmosphere, photolysis was operating on vastly more material. The the freed hydrogen atoms faced a second physical process called hydrodynamic escape. Hydrogen is the lightest element in the periodic table, a single proton paired with a single electron. In the upper atmosphere of a planet like Venus, where solar radiation and the solar wind pour enormous energy into the gas, hydrogen atoms move fast. They bounce and collide and gain thermal energy from the energetic photons raining down from the sun. For an atom as light as hydrogen, that thermal energy can be enough to exceed the planet's escape velocity, the speed required to permanently leave the gravitational grip of the planet and stream out into space. The effect is not random, atom by atom loss, but a bulk outflow, a wind of hydrogen streaming away from the planet in coherent, organized quantities, driven by the energy cascade from the young, energetic sun. Heavier atoms like oxygen, nitrogen, and deuterium cannot escape this way. They are too massive for the thermal energy to push them past escape velocity. So they remain accumulating, while the lighter, ordinary hydrogen bleeds away. The oxygen atoms left behind by photolysis did not simply linger in the atmosphere. Oxygen is chemically reactive, and at the high temperatures that Venus's surface was reaching, it combined with surface rocks in oxidation reactions, or reacted with sulfur compounds in the atmosphere to form sulfur dioxide and other compounds. The oxygen was consumed. The result was an atmosphere being systematically stripped of its hydrogen and therefore of its capacity to hold or make water, while the heavier components accumulated. This process, photolysis, followed by hydrodynamic escape of hydrogen, operated for hundreds of millions of years. It would have been operating on every world in the inner solar system's history. But the rate of the process depends critically on how much water vapor is reaching the upper atmosphere, which depends on how warm the surface is, which depends on how strong the greenhouse effect is. On Earth, the process is slow and minor because the cold trap keeps water vapor away from the upper atmosphere. On Venus, once the warming began to push above certain temperature thresholds, the process accelerated dramatically. Then, in May of 2024, a team led by Michael Chaffin and Erin Kangi at the University of Colorado Boulder published a paper in the journal Nature that added a mechanism to this story that had gone entirely unrecognized for decades. The molecule at the center of their discovery is called HCO+, known to atmospheric chemists as protonated formilium. It forms in the upper atmosphere of Venus when carbon dioxide, which was abundant in Venus's early atmosphere from volcanic outgassing, reacts with water vapor under the influence of energetic solar radiation. Carbon dioxide and water vapor combine through a sequence of ion chemistry reactions to produce this HCO+ ion. When HCO+ then encounters a free electron in the ionosphere and undergoes a process called dissociative recombination, a splitting reaction driven by the electron's capture, one of the products is a hydrogen atom, moving with enough velocity to escape Venus's gravitational field entirely. No previous spacecraft had been specifically designed to measure HCO+ concentrations in Venus's atmosphere. The instrument aboard Pioneer Venus had not been looking for it. Decades of atmospheric modeling had not included this reaction pathway. It was sitting in the chemistry the entire time, operating continuously, ejecting hydrogen from the atmosphere without anyone noticing. Chaffin, Kangi, and their colleagues demonstrated its existence by analyzing the Pioneer Venus atmospheric measurements. Indirectly, the raw ingredients that produce HCO+ were present in the data, and then modeling the production and loss rates of the ion, given what we know about Venus's ionosphere. Their conclusion: this mechanism, operating alongside the previously known pathways of photolysis and direct thermal escape, likely doubled the rate at which Venus was losing hydrogen throughout its history. Doubling the escape rate has a direct consequence for the timeline. If water was escaping twice as fast as previous models assumed, the planet's water inventory was exhausted in roughly half the time those models predicted. The team estimated that Venus could have lost all of its water in approximately 600 million years, a geologically fast interval. 600 million years is not nothing. On Earth, the first 600 million years saw the formation of the oceans and possibly the first emergence of microbial life. But it is substantially less than the 2 to 3 billion year habitable window suggested by the most optimistic climate simulations. The HCO+ discovery does not eliminate the possibility of a Venusian habitable era, but it potentially constrains it to an earlier and shorter window than some models implied. This is currently a leading hypothesis interpretation, not a confirmed fact. Direct measurement of HCO+ in Venus's atmosphere, which Da Vinci is designed to attempt, will be needed to confirm the mechanism's actual magnitude and contribution. But the chemistry is sound. The indirect evidence from Pioneer Venus data is consistent, and the publication in Nature represents peer-reviewed, expert-reviewed science from a NASA-supported research group. Now, with the water gone, the second catastrophic process engaged with nothing to stop it. On Earth, there is a planetary-scale chemical cycle that has regulated atmospheric carbon dioxide for at least 4 billion years. Planetary scientists call it the carbon silicate cycle, and understanding it is not optional for understanding why Earth survived what Venus did not. The cycle is a closed loop involving the atmosphere, the ocean, the surface rocks, and the deep interior, and it operates as Earth's long-term climate thermostat. When temperatures rise, the cycle draws CO2 out of the atmosphere, cooling the planet. When temperatures fall, the cycle lets CO2 accumulate, warming it again. It has kept Earth within the range of liquid water stability through changes in solar luminosity, through volcanic catastrophes, through ice ages, through everything the planet has thrown at itself over geological time. Here is how the cycle operates. Carbon dioxide in the atmosphere dissolves in rainwater to form a weak carbonic acid solution. Acidic rainwater falls on silicate rocks, basalt, granite, feldspar, the kinds of rock that make up the bulk of Earth's surface, and chemically weathers them. This weathering reaction releases calcium and magnesium ions and carbonate ions into the water, which rivers carry to the sea. In the ocean, organisms from corals to microscopic plankton use those dissolved calcium and carbonate ions to construct their shells and skeletons. When those organisms die, their carbonate structures sink, accumulate on the ocean floor, and over millions of years form thick layers of limestone and chalk. Plate tectonics then carries those carbonate-rich seafloor layers into subduction zones, where one tectonic plate dives beneath another and plunges into the mantle. The heat of the mantle breaks the carbonates down, releasing carbon dioxide, which then returns to the atmosphere through volcanic outgassing at subduction zones and mid-ocean ridges. The loop is closed. Carbon that was in the atmosphere, as CO2, passes through the ocean, through marine organisms, through the seafloor, into the mantle, and back out to the atmosphere, all driven by plate tectonics and liquid water working together. The thermostat function works through a specific feedback mechanism. When surface temperatures rise, the weathering reaction accelerates. Warm, wet conditions break down rocks faster and draw more CO2 out of the atmosphere. As CO2 decreases, the greenhouse warming decreases, and temperatures fall back toward equilibrium. When temperatures fall, weathering slows, volcanic outgassing continues at its background rate, CO2 builds back up, and temperatures rise again. The system counteracts its own deviations from equilibrium, stabilizing around a temperature that keeps liquid water on the surface. This is a textbook negative feedback loop, the kind that stabilizes rather than destabilizes, and it has been running on Earth for most of its history. This cycle requires two things to operate: liquid water, to drive the weathering reaction that draws CO2 out of the atmosphere, and plate tectonics, to subduct the carbonate sediment back into the mantle and close the loop. Venus lost its liquid water. That alone would have been enough to break the weathering step of the cycle. Without water to dissolve CO2 and fall as rain on silicate rocks, the carbonate formation step of the cycle simply stops. CO2, outgassed by volcanoes, has no mechanism to re-enter the rocks. It accumulates in the atmosphere. But there is a second dimension to Venus's tectonic history that makes the story more complex and more consequential. Whether Venus today lacks plate tectonics because it never had them, because it lost them when water was lost, or because its geological evolution followed a fundamentally different trajectory than Earth's, this remains one of the central unresolved questions in planetary science. The Magellan spacecraft found no global pattern of plate margins or subduction zones on Venus's surface. The surface has a roughly uniform age, suggesting it was last reshaped in a relatively recent geological episode, possibly a catastrophic global resurfacing event somewhere between 200 million and 1 billion years ago, rather than the continuous seafloor, spreading and consumption that characterizes Earth. This is consistent with what scientists call stagnant lid tectonics, in which the entire crust acts as a single rigid shell over a convecting interior, rather than the mobile lid tectonics of Earth, where the crust is broken into moving plates. A 2023 study examining Venus's current atmospheric composition found that the observed abundances of nitrogen and carbon dioxide in the present-day atmosphere could not be explained by a stagnant lid. History alone that an early phase of plate tectonic-like activity was required to produce the outgassing patterns that built the atmosphere. If that interpretation is correct, Venus may have had mobile lid tectonics early in its history, and then lost them potentially because the loss of water removed the lubrication that water provides to tectonic plate motion, causing the plates to lock. If true, Venus once had both the liquid water and the plate tectonics needed for a functioning carbon silicate thermostat, and losing one caused it to lose the other, triggering the runaway CO2 accumulation. This is a hypothesis, not a confirmed chain of events, but it illuminates the potential interdependence of habitability's key systems. Water and plate tectonics may not be independent prerequisites for habitability. They may be mutually sustaining. Lose one, and you lose the other, and losing both means losing the thermostat. Without either liquid water or a functioning tectonic cycle to remove CO2 from the atmosphere, billions of years of volcanic outgassing added carbon dioxide continuously to the Venusian atmosphere with no counterbalancing removal pathway. The greenhouse warming increased. Surface temperatures climbed. Any remaining surface water, if any survived into this phase, boiled away into the atmosphere, where it was photolyzed and its hydrogen escaped. The warming caused whatever rock atmosphere reactions existed to slow or stop. The CO2 that was being added outpaced any mechanism that might have removed it. The atmosphere thickened, the pressure rose, the temperature rose further. This is not a rapid process. It operated over hundreds of millions to billions of years, but it operated without any mechanism to reverse it, without any stabilizing feedback to counteract it, and therefore it simply continued until the system reached the state we observe today. 93 bars of pressure, 465 degrees Celsius, 96% carbon dioxide, not a drop of liquid water anywhere on or near the surface. Now consider the scale of what the current Venusian atmosphere represents. The entire mass of Earth's oceans is approximately 1.4 billion kilograms of water. If Venus originally had a comparable amount of water, which the isotope evidence is at least consistent with, and lost it over hundreds of millions to perhaps 2 billion years through the mechanisms described, then the ocean of a planet was converted, atom by atom, into an escape of hydrogen to space and an accumulation of oxygen in rocks. And simultaneously, over the same geological timescale, the equivalent of Earth's ocean of water in CO2 was being poured into Venus's atmosphere by its volcanoes, with no ocean to absorb it, no weathering to remove it, no subduction cycle to sequester it. The result is an atmosphere that is 92 bars of pure carbon dioxide sitting above a surface that radiates heat outward at a rate dictated by a temperature of 465 degrees Celsius, balanced by the extraordinary thickness of the overlying atmospheric blanket. This is not a planet that got a little too warm. This is a planet where the entire climate regulatory system was dismantled, step by step, in a sequence that followed necessarily from conditions that were not dramatically different from Earth's. There is one final point about this cascade that belongs in this part of the story, before we go down to the surface itself. It concerns reversibility, or the complete and total absence of it. Once Venus had lost its water, the cascade could not reverse. Reversing it would require reintroducing liquid water to the surface to restart the weathering reaction. But the surface temperature of 465 degrees Celsius would instantly boil and vaporize any water before it could contact the rocks. Reversing it would require the CO2 to be removed from the atmosphere by some mechanism, but without liquid water and without subduction, there is no mechanism. Even if a hypothetical future impact delivered a new supply of water to Venus, as some models of early planet formation suggest may have happened to all the terrestrial planets, that water would be vaporized on contact with the 465 degrees surface, enter the atmosphere, and be photolyzed and lost to space within a geologically brief interval. The planet cannot reset. The cascade, once run, is final. This is what makes the Venus story so different from the Martian story, where scientists debate whether ancient habitable conditions could theoretically return if Mars were somehow warmed. Mars lost its atmosphere slowly, over billions of years, through a process of gradual atmospheric escape after its magnetic field weakened. The situation is potentially reversible in principle, even if not in practice. Venus's situation is not reversible in principle. The thermostat has been destroyed, the regulatory system has been dismantled, and the planet is now locked into a state that has no exit ramp. There is something on the other side of that locked surface, though. Something that the planetary scientists who study Venus have confirmed only recently, and that changes the picture of what Venus actually is: not a dead world, frozen in its catastrophe, but something stranger and more active than that. something that the Soviet Union's most extraordinary engineers barely glimpsed through the windows of probes they knew were going to die, and that 3 decades of archived radar images are only now beginning to reveal. The surface of Venus is still alive. And what that means for understanding this planet, and for the faint, unresolved, deeply contested possibility of something still existing within its corrosive clouds, is where this story goes next. Come in low over Venus at orbital altitude, 250 kilometers above the surface, and what you see is nothing, not darkness, not the structured complexity of a clouded but translucent sky, but an absolute, sealed, cream-colored wall stretching from horizon to horizon, pole to pole, without a single gap. There are no gaps in the Venusian cloud deck. There have never been gaps. The planet is wrapped in a continuous, unbroken shell of cloud that reflects approximately 70% of all incoming sunlight directly back into space, a reflectivity called albedo, higher than any other planet in the solar system. This is why Venus blazes so brightly in Earth's night sky. It is not close proximity. It is the mirror finish of billions of tons of sulfuric acid aerosol suspended in a continuously replenished, globally uniform layer between approximately 50 and 70 kilometers altitude, acting as the most efficient solar reflector in the inner solar system. Those clouds are not water. They are not ice. They are droplets of concentrated sulfuric acid, formed when sulfur dioxide, released by Venus's volcanoes, reacts with the small quantity of water vapor remaining in the atmosphere under the influence of ultraviolet radiation. The acid exists in concentrations between 75 and 96% by mass, in some regions far more corrosive than the dilute sulfuric acid used in car batteries, which sits at around 37%. Any metallic instrument, not specifically designed to survive it, begins corroding within minutes. Any organic material dissolves faster than that. The cloud deck is not merely a visual barrier. It is a chemically aggressive environment that has destroyed or degraded instruments on every probe that has passed through it. Below the clouds, the atmosphere transitions. The sulfuric acid aerosol thins below about 48 kilometers as temperatures rise above the acid's stability range. Between 48 and 30 kilometers, the air is clearer but thick with carbon dioxide at pressures approaching 20 to 30 bars, still far above anything on Earth's surface. The light filtering down from above has been scattered and rescattered through the acid layer until it arrives at the lower atmosphere as a diffuse, dim, orange-tinted glow stripped of its blue wavelengths, resembling something between a deep overcast and the light at the bottom of a shallow sea. At 30 kilometers, the temperature reads above 200 degrees Celsius. At 20 kilometers, above 300. At 5 kilometers above the surface, temperatures approach 400 degrees and pressures approach 70 bars. And at the surface itself, where the carbon dioxide atmosphere reaches its full depth, an atmosphere approximately 90 times as massive as Earth stacked above every square meter of rock, the pressure is 93 bars. The temperature is 465 degrees Celsius. And the combined effect is an environment that no material humans have yet engineered can survive in for more than a few hours. The only machines that have ever stood on that surface and returned information about it were the Soviet Venera landers, a series of spacecraft developed by Soviet engineers from the mid-1960s through the 1980s in one of the most technically audacious programs in the history of space exploration. The engineers who designed them worked with a specific and sobering constraint. The landers were going to die. The only variable was how much data they could transmit before the planet killed them. The challenge was not just thermal, not just keeping the electronics cool enough to function when the air outside was 465 degrees, but structural. The pressure at Venus's surface would crush an ordinary aluminum pressure vessel in minutes. The Venera landers were built as thick-walled titanium spheres, pre-cooled before entry, insulated with multiple layers of heat-resistant material, and designed to operate long enough to complete their primary measurements before the heat penetrated the insulation and destroyed the electronics. The first lander to successfully return data from the surface was Venera 7, which touched down in December 1970, survived for approximately 23 minutes, and transmitted temperature and pressure measurements confirming what models had predicted. The surface was approximately 465 degrees Celsius, under approximately 90 atmospheres of pressure. The data it returned settled a debate that had persisted in the scientific community about whether the Venusian surface conditions were truly as extreme as theory predicted. They were exactly that extreme. Venera 9, in October 1975, returned the first photographs ever taken from the surface of another planet beyond the Moon. What the camera revealed was unexpected in a specific and scientifically important way. The rocks in the image were angular, sharp-edged, slab-like. They had not been rounded by prolonged erosion the way ancient rocks on Earth smooth out over millions of years of exposure to wind and water. They looked fresh, geologically young, as if they had been emplaced relatively recently, rather than sitting undisturbed for billions of years. Venera 10, landing a few days later at a different site, showed older, more rounded terrain. The contrast between the two sites was immediately informative. Venus has geological regions of different ages, meaning its surface has been actively reshaped at different times and rates in different locations, not uniformly aged, as a single episode of resurfacing would produce. Venera 13, landing in March 1982, holds the survival record that stands today, approximately 2 hours and 7 minutes. In that window, it returned color images of the surface, conducted soil composition analysis using X-ray fluorescence spectroscopy, recorded sounds from the Venusian surface, the first sound recording from another planet, and transmitted atmospheric composition measurements taken during descent. The color images showed a landscape of flat, layered, dark basaltic rock and fine-grained reddish-brown sediment, lit by an orange-tinted ambient light filtered through dozens of kilometers of dense atmosphere and acid cloud above. The compositional analysis identified the surface rock as similar to terrestrial basalt, the same kind of dark volcanic rock that forms Earth's oceanic crust and emerges from shield volcanoes like those in Hawaii. The comparison was not trivial. It said something fundamental. Venus's surface geology is volcanic, mafic, and in composition, not unlike what you would find on the floor of Earth's oceans, exactly what you would expect from a planet with an active mantle churning beneath. 2 hours and 7 minutes. The planet destroyed Venera 13 in exactly the time it took the Soviet engineers' thermal insulation budget to be consumed. The lander's electronics overheated and failed. The planet had won, as it always wins, but not before giving up more information about itself than any probe had previously extracted. Now, decades after those Soviet missions, a different kind of instrument has revealed something about Venus that no lander and no atmospheric probe could have detected on its own. The surface is still being made, not preserved from billions of years ago, not frozen in its post-catastrophe state, but actively rebuilt by processes still operating in the present geological moment. In the spring of 2023, planetary scientists Robert Herrick at the University of Alaska Fairbanks and Scott Hensley at NASA's Jet Propulsion Laboratory published the results of a painstaking comparison they had made between radar images of the same region of Venus taken at two different times during the Magellan mission. Magellan had orbited Venus from 1990 to 1994, mapping approximately 98% of the planet's surface with synthetic aperture radar, a technique that bounces radar pulses off the surface and uses the return signal to construct detailed maps of terrain and surface texture capable of penetrating the cloud deck that blocks all optical imaging. The images it generated remain the most detailed views of Venus's surface ever obtained. Herrick and Hensley compared Magellan images of a volcanic vent on the northern flanks of Mount Mons, Venus's tallest volcano, at approximately 9 kilometers above the mean planetary radius and the planet's second highest mountain overall, taken in February 1991 and again in October of the same year, 8 months apart. In the February image, the vent was an approximately circular depression covering roughly 2.6 square kilometers. In the October image, the same vent had changed. It was now irregular in outline, enlarged to approximately 3.9 square kilometers, with the surrounding terrain showing characteristics consistent with fresh material having been emplaced from below. The change was not ambiguous. Something had happened to that vent between February and October of 1991. The most consistent explanation, after ruling out instrument artifacts and viewing geometry differences, was that the vent had partially filled with molten lava from a subsurface source and then partially subsided as the magma drained or cooled, the surface expression of a volcanic eruption observed in progress, preserved in archived radar data for more than 30 years before anyone compared the two images closely enough to notice. This was the first direct observational evidence of active volcanism on Venus. Not a model prediction, not a statistical inference from crater densities or surface chemistry, but a before and after photograph of a volcano in the act of erupting. The following year, in May 2024, the planetary science community received a second, independent confirmation. A team led by Davide Solcanis at the Università d'Annunzio in Pescara, Italy, published a study in Nature Astronomy using a different analytical approach to the Magellan archive. Rather than comparing individual feature outlines, Solcanis and colleagues mapped changes in radar backscatter, the intensity with which surfaces reflect radar pulses across broad volcanic flow fields between different Magellan observation periods. Changes in radar backscatter in volcanic terrain are particularly diagnostic. Fresh lava flows, still rough and glassy at the scale of radar wavelengths, produce strong and distinctive backscatter signatures compared to older, weathered flows. The team identified 2 regions showing changes consistent with new lava flow emplacement during the Magellan mission itself. The first was on the western flank of Sif Mons, a large shield volcano in the Isla Reggio highland region of Venus. The second was in an area of low-lying volcanic plains called Niobe Planitia. At Sif Mons, the new material covered approximately 30 square kilometers, enough rock, as the team calculated, to fill the volume of approximately 36,000 Olympic-sized swimming pools. At Niobe Planitia, the emplaced volume was larger still, approximately 45 square kilometers of new rock, equivalent to filling roughly 54,000 Olympic pools. Both eruptions appear to have occurred during the 1990 to 1992 observation window, sitting in the archive unrecognized for more than 3 decades. What do these eruptions tell us about Venus today? Several things, each significant and none of them available from the pre-2023 picture of the planet. First and most directly, Venus's interior is still hot enough to produce magma and drive it to the surface. The decay of radioactive isotopes, primarily uranium-238, thorium-232, and potassium-40 in Venus's mantle and crust releases heat continuously, as it does in Earth's interior. That heat drives mantle convection, the slow, solid-state flow of mantle rock from hotter depths toward cooler, shallower regions, creating the rising plumes and sinking slabs that power geological activity at the surface. For Venus to be producing eruptions at a rate that left detectable fresh lava flows in an 8-month observation window in the early 1990s, the interior heat engine must still be running at a rate comparable, in some respects, to Earth's geological activity. The planet has not thermally died. Second, those eruptions release gases into the atmosphere. Sulfur dioxide, carbon dioxide, water vapor, hydrogen sulfide, and other volcanic compounds are pumped into the Venusian atmosphere each time an eruption occurs. The sulfuric acid cloud deck itself, the defining visual feature of Venus, is maintained in part by volcanic sulfur dioxide reacting with the atmospheric water vapor that reaches the upper cloud layer. Without continued volcanic input, the clouds would gradually thin and change character over geological timescales as the sulfur compounds were rained out or chemically transformed. That the clouds are still there, still globally uniform, still dense enough to make Venus the most reflective planet in the solar system, is itself a sign that volcanism is ongoing. Third, and most important for understanding what kind of world Venus actually is, the frequency implied by the new detections is higher than expected. Herrick's estimate, based on the Mars vent change alone, suggests eruptions on Venus may occur roughly every few months, comparable in frequency to volcanic activity at active sites on Earth, such as Kilauea in Hawaii or the volcanic systems of Iceland. Sulcanis's additional detections reinforce this picture. Venus is not a planet that erupts occasionally in geological terms. It may be erupting on timescales that, if you were watching with the right instruments, you could observe directly. It may be one of the most volcanically active worlds in the inner solar system. Related to this volcanism is a class of surface feature that reveals something about the mechanism driving it. Coronae are large, ring-shaped structures on Venus's surface, circular to oval depressions or elevated regions, surrounded by concentric rings of ridges and fractures, formed when hot mantle plumes push up against the underside of the lithosphere from below. The plume heats and softens the overlying rock, causes the surface to dome upward. Then, as the plume material spreads laterally and cools, the center of the dome subsides, leaving the ring of deformed terrain as a permanent surface record of where the plume acted. Coronae range from roughly 100 to more than 500 kilometers in diameter, and are found across Venus's surface in numbers and distribution that suggest widespread, ongoing mantle activity. Research combining three-dimensional thermomechanical modeling with surface mapping notably work from groups at the University of Maryland and ETH Zurich found evidence that at least 37 coronae on Venus show morphological characteristics consistent with active or geologically recent plume activity, meaning the mantle processes that form them are not ancient and finished, but ongoing within the last few million years. In geological time, that is now. The coronae are windows into a mantle that is still convecting, still delivering heat toward the surface, still reshaping the crust from below. Together, the confirmed lava flows, the active vents, the geologically fresh coronae, these observations build a portrait of Venus that is the opposite of what many planetary scientists assumed for decades. Venus is not a thermally dead relic. Its geological clock stopped at the moment of its catastrophic atmospheric transformation. Venus is a geologically living world. Its interior is churning. Its volcanoes are erupting. Its surface is still being made. The catastrophe that destroyed its habitability did not stop the planet's engine. It only destroyed the regulatory systems that could have kept the engine from producing a runaway outcome. This geological vitality is directly relevant to what lives or what may live in the one layer of Venus's atmosphere that has drawn more attention from astrobiologists than any other feature of the planet. Not the surface, not the deep mantle, the clouds. Between approximately 48 and 60 kilometers above Venus's surface, the temperature and pressure conditions are, in a narrow physical sense, the most Earth-like in the solar system outside of Earth itself. At 55 kilometers altitude, the temperature is approximately 25 degrees Celsius, and the pressure is approximately 1 bar, conditions that, stripped of their chemical context, would not be out of place in a pleasant summer afternoon in a temperate climate on Earth. This coincidence of temperature and pressure has led researchers to consider whether the Venusian cloud layer, despite its sulfuric acid composition, might harbor extremophile microbial life organisms that have evolved mechanisms to tolerate or even exploit the acidic environment. This is where the story gets genuinely complicated and where the distinction between candidate signal and confirmed fact becomes essential to maintain. In September 2020, a team led by Jane Greaves at Cardiff University published a paper in Nature Astronomy reporting a tentative detection of phosphine in Venus's atmosphere. The detection was made using radio telescope observations from the James Clerk Maxwell Telescope in Hawaii and the ALMA Telescope Array in Chile. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, is produced on Earth primarily by biological activity. Certain anaerobic bacteria generate it as a metabolic byproduct. Industrial chemistry also produces it. But in the reducing atmosphere of a gas giant like Jupiter or Saturn, phosphine can be synthesized abiotically by the extreme temperatures and pressures of the deep atmosphere and then transported upward. In the oxidizing, sulfuric acid-dominated atmosphere of Venus, however, known abiotic chemical pathways for phosphine production are either absent or insufficient to produce the concentrations that Greaves's team initially reported. The paper was careful in its framing. It did not claim life had been detected, only that a chemical signal was present that could not be explained by known atmospheric chemistry, and that biological production was one possible explanation. But the implication was clear, and the reaction from the scientific community was immediate. Multiple independent teams reanalyzed the radio telescope data. Results were mixed. Some confirmed that a phosphine signal was present, though at lower concentrations than originally reported. Others argued the signal was within the noise level of the instruments and might not be real. A significant concern emerged around the subtraction of sulfur dioxide from the spectrum. Sulfur dioxide produces absorption features at wavelengths close to those of phosphine, and the way that subtraction was performed affected the residual signal attributed to phosphine. The original paper was revised. Confidence levels were lowered. The claimed phosphine abundance dropped from approximately 20 parts per billion to values closer to 1 to 4 parts per billion in subsequent analyses, with some analyzers finding no statistically significant detection at all. A tentative detection of ammonia, a molecule with similarly problematic abiotic origins in Venus's oxidizing atmosphere, was reported by the same Cardiff-led research group at the UK National Astronomy Meeting in 2024, adding a second candidate signal to the picture without resolving the first. As of the time this documentary was produced, the scientific status of both detections is genuinely unresolved. The phosphine claim has not been confirmed at a level that satisfies the scientific community's standard for a robust detection. It has not been definitively ruled out. The ammonia detection is even more preliminary. Both are candidate signals, real enough to warrant further investigation, not established enough to serve as the basis for conclusions about habitability or biology. The researchers proposing the Verve mission concept, Venus Life Finder, presented their concept at the Royal Astronomical Society's National Astronomy Meeting in 2025, specifically to provide direct, in situ chemical sampling of the cloud layer that would resolve these detections one way or another. The mission is conceptual, not yet selected or funded. What makes this debate scientifically interesting, beyond the obvious headline appeal of possible life in Venus's clouds, is what it reveals about the limits of remote sensing. The phosphine and ammonia signals, if real, cannot be explained by any atmospheric chemistry model that uses currently known reactions and currently measured abundances of Venus's atmospheric constituents. Whether that means the models are missing something chemical, or whether the signals are instrumental artifacts, or whether they reflect something genuinely anomalous in the cloud layers, chemistry, biological, or otherwise, cannot be determined by telescope observations alone. The cloud layer of Venus is chemically active in ways that are not fully characterized, driven by a complex interplay of volcanic inputs, solar photochemistry, and sulfur cycle reactions. There may be unknown abiotic processes producing these gases. There may be errors in the observations. There may be something biological. The current data cannot distinguish between these possibilities. What the detections have accomplished, regardless of their ultimate interpretation, is to refocus attention on the cloud layer as a target of scientific interest in its own right, not as an obstacle to reaching the surface, but as an environment worthy of direct investigation. And that refocusing is timely, because the cloud layer contains other mysteries that have nothing to do with biology and everything to do with atmospheric dynamics that remain poorly understood. The Venusian cloud deck rotates around the planet approximately 60 times faster than the surface below it. At the cloud tops, approximately 70 kilometers altitude, winds reach approximately 360 kilometers per hour, completing a full circumplanetary circuit in roughly 4 Earth days. The surface below, rotating at its extraordinary rate of once every 243 Earth days, barely moves by comparison. This phenomenon, called atmospheric superrotation, has been observed in Venus's atmosphere since the Soviet Venera missions in in the 1970s and has been studied by Japan's Akatsuki spacecraft, which entered Venus orbit in 2015 and operated until contact was lost in late 2024. Despite decades of observation, the physical mechanism that sustains superrotation at this intensity is not fully understood. Multiple atmospheric models can reproduce it, but with different combinations of mechanisms: momentum input from solar tides, wave propagation from the lower atmosphere, thermally driven circulation, none of which has been conclusively identified as the primary driver. The cloud deck is not a passive shell. It is a dynamically complex, energetically maintained atmospheric system that is still presenting fundamental questions to the scientists who study it. Beneath that dynamic sky, on a surface that is still being built by volcanoes, whose eruptions leave fresh rock across tens of square kilometers while spacecraft orbit above, Venus is not the static monument to catastrophe that it might appear. It is active, vigorous, geologically alive, and in its cloud layer, potentially harboring chemical complexity that goes beyond current models, whether that complexity involves biology or not. The planet that lost everything above its surface still has, beneath the depth, an engine that has never stopped running. And the questions that engine raises about where geological energy goes without plate tectonics, about how a planet can be volcanically prolific and simultaneously bereft of the thermostat that would make that volcanism life-sustaining, rather than irrelevant, point directly toward what Venus can teach us about the nature, planets in general, and about worlds around other stars in particular. When the Kepler Space Telescope completed its primary mission and scientists sat down to work through the data, it had collected over 4 years of staring at a patch of sky roughly the size of your hand held at arm's length. What they found changed the fundamental accounting of what the galaxy contains. Kepler had detected thousands of planets transiting across the faces of distant stars, and when the statistics of those detections were analyzed and extrapolated to the full population of stars in the Milky Way, the conclusion was stunning. Roughly 1 in 5 Sun-like stars hosts a planet roughly Earth-sized in or near the habitable zone. Apply that fraction to the approximately 200 billion stars in our galaxy, and the implied number of potentially Earth-like worlds runs into the tens of billions. The galaxy is not barren. It is overwhelmingly rich in rocky, roughly Earth-sized planets sitting at the right distance from their suns to potentially have liquid water on their surfaces. The discovery prompted an enormous research effort aimed at a simple question: of all those planets, how many are actually habitable? And it is here, at precisely this question, that Venus becomes the most important planet in the solar system, for reasons that have nothing directly to do with whether it was once inhabited or whether anything still lingers in its clouds. Venus is important because of what it tells us about the single most dangerous assumption in exoplanet science: that Earth-sized plus habitable zone equals habitable world. It does not. Venus is the proof. Understanding what Venus tells us about that failure and how the 3 missions being built to study it will transform the precision of our answer requires working through what we actually need to know about an exoplanet to determine whether it is genuinely habitable, and why almost none of those things are currently measurable from the instruments we have. The habitable zone itself is a starting point, not an answer. The concept was introduced in the early 1990s as a framework for estimating which orbital distances from a star could allow a rocky planet to maintain liquid water on its surface, given what was then understood about planetary atmospheres and greenhouse effects. The The framework worked by calculating the incoming stellar flux at which the greenhouse warming of a CO2 water atmosphere would either freeze all surface water at the outer boundary or trigger a runaway greenhouse at the inner boundary. Those two boundaries define the zone. For our solar system, the inner boundary sits somewhere between Venus's orbit and Earth's, and its precise location depends critically on how the runaway greenhouse threshold is modeled, which in turn depends on how water vapor behaves as a greenhouse gas in warming atmospheres, how clouds form and change as temperatures rise, and how quickly water escapes from an increasingly hot upper atmosphere. Venus sits at approximately 72% of Earth's orbital distance from the Sun. It receives approximately 1.9 times Earth's solar flux. Whether that puts it inside or outside the true inner boundary of the habitable zone has been debated since the concept was introduced, and the answer depends on which physical processes you include in the model. Earlier, simpler models placed the inner boundary at approximately 95% of Earth's orbital distance inside Venus, outside Earth, and concluded that Venus was doomed from the start. More sophisticated three-dimensional models incorporating realistic cloud dynamics, like those produced by Michael Wei's group, suggested that a slowly rotating planet with liquid water could remain habitable even at Venus's current flux level, pushing the effective inner boundary inward. Other models incorporating constraints from oxygen loss rates and argon degassing concluded that only a narrow range of early conditions on Venus could have led to any habitable period at all. This spread of model results is not a failure of computation. It reflects genuine physical uncertainty about how the key processes work. And that uncertainty matters enormously for exoplanet science, because every potentially Earth-like world discovered by Kepler, by TESS, by radial velocity surveys, every planet reported as sitting in its star's habitable zone, has had its habitability assessed by comparing its orbital flux to a model-derived inner boundary that still carries substantial uncertainty. If the true inner boundary is where the optimistic models place it, then many planets currently considered borderline may in fact be habitable. If the true inner boundary is where the pessimistic models place it, many of those planets are Venus's geologically transformed, runaway greenhouse worlds that we are labeling as candidates for life without the physical basis to justify that label. Venus, studied closely enough by the right instruments, can calibrate those models in a way that no amount of additional exoplanet observation can replace. The planet is the solar system's own laboratory for the runaway greenhouse threshold. Direct measurement of Venus's atmosphere, its current chemical composition from the noble gas abundances that record its entire geological history, its water isotope ratios that document the trajectory of its water loss, the chemistry of its cloud, layer, and lower atmosphere will constrain the models that determine where the inner boundary of the habitable zone actually falls. Tighten those constraints by even 20%, and the list of truly promising exoplanet candidates changes substantially. The science of finding life in the universe depends on knowing what Venus knows, and retrieving what Venus knows requires sending instruments there. This is what drives NASA's DaVinci mission, whose full name, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, encodes its scientific priorities with unusual directness. Noble gases are the chemical fingerprints of planetary history. Helium, neon, argon, krypton, and xenon do not react chemically with anything in an atmosphere or on a surface. Once outgassed from a planet's interior through volcanism, they stay in the atmosphere essentially forever. Their relative abundances encode information about the planet's bulk composition, its accretion history, how much volatile material it received from the outer solar system versus the inner, and how its atmosphere has been modified by escape over geological time. Comparing Venus's noble gas signature to Earth's, Mars's, and to the compositions of various classes of meteorites that represent primitive solar system material will tell scientists what Venus was made of at the beginning and what happened to its volatiles over the subsequent 4.5 billion years. That comparison, done with the analytical precision that only direct atmospheric sampling can provide, is currently impossible with any instrument at Earth or in Earth orbit. Da Vinci will deliver a spherical probe approximately 1 meter in diameter through Venus's atmosphere over a descent of approximately 55 to 60 minutes from the base of the cloud deck at approximately 61 kilometers altitude to a few kilometers above the surface, taking atmospheric measurements continuously throughout. The probe will also carry cameras for the first high-resolution imaging of Venus's surface from within the atmosphere itself, targeting a highland region called Alpha Regio, which some researchers believe may preserve rocks compositionally distinct from the surrounding volcanic plains, rocks that could carry the chemical signature of ancient water-rock interaction at the surface. Da Vinci's preferred launch window falls in the late 2030s if funding allows it to proceed on schedule, though as of the spring of 2026, the mission was receiving approximately $99 million in fiscal year 2026 appropriations, enough to maintain development, but not sufficient to guarantee the timeline against further budget pressure. The mission remains funded and progressing, with its full resource allocation subject to the constraints of NASA's broader Planetary Science Division budget. NASA's Veritas mission Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy approaches Venus from orbit rather than through the atmosphere, using a synthetic aperture radar, substantially more powerful than the Magellan instrument that mapped the surface in the early 1990s, where Magellan produced surface maps at resolutions between approximately 75 meters and a few kilometers. Veritas is designed for resolutions approaching approximately 30 meters globally and far finer for targeted regions, combined with interferometric radar capable of measuring surface elevation changes to centimeter precision. This is the resolution at which geological history becomes readable, where the boundaries between ancient and young lava flows become distinguishable, where the structural expressions of different tectonic regimes become identifiable, where the question of whether Venus ever had mobile lid tectonics has a chance of being answered from orbit. Veritas also carries an infrared spectrometer designed to probe the surface composition through the narrow atmospheric windows, where the lower atmosphere is partially transparent to thermal infrared radiation, the same windows that allow Venusian surface temperatures to be mapped from Earth. The spectrometer will search for compositional differences between the highland regions and the surrounding lowland plains, looking for the mineralogical signatures that would indicate ancient continental crust-style rock versus the basaltic volcanism that dominates most of Venus's surface. If Venus's highland regions contain rock compositions consistent with ancient continental material, granite and related rocks that require the sustained interaction of water with silicate magma to form, that would be direct evidence of ancient water rock chemistry on a scale that implies sustained surface liquid water at some point in the planet's history. Veritas was selected in 2021, placed in a holding pattern in 2022 following institutional difficulties at JPL, and reinstated into the NASA budget in 2025, with a target launch no earlier than 2031. As of 2026, it is progressing at a constrained pace, with its schedule remaining dependent on budget allocations still being finalized. ESA's Envision, formally adopted for development by ESA's Science Program Committee in 2024, rounds out the fleet with capabilities that complement both Da Vinci and Veritas without duplicating them. Envision will carry a subsurface sounding radar capable of probing the upper few hundred meters of Venus's crust, looking at the layering and structure just beneath the surface, information about how the crust is organized, how volcanic material has been emplaced over time, and whether there are structural differences between geological units that would help distinguish tectonic regimes. Envision's atmospheric spectrometers will monitor trace gas abundances in the upper atmosphere continuously over the mission's operational period, providing time series data on how atmospheric chemistry varies, particularly relevant to the question of whether volcanic outgassing is adding detectable chemical signatures that change with volcanic episode timing. And the mission will carry a NASA-provided synthetic aperture radar instrument, though the status of that NASA contribution was under active review in the context of proposed budget reductions as of 2026. Envision is targeting a launch in November 2031 aboard an Ariane 6-4 rocket, with science operations beginning approximately 3.5 years later after the transit to Venus and an aerobraking phase to reach the final science orbit. Together, if all three missions fly on timelines close to what is currently planned, Da Vinci, Veritas, and Envision will constitute the most comprehensive coordinated investigation of a single planet in the history of planetary science. The chemical fingerprint of Venus's history from Da Vinci, the geological map of its surface from Veritas, the subsurface structure and atmospheric chemistry evolution from Envision. Between these three datasets, the question of whether Venus was ever habitable moves from a modeling exercise constrained by limited data to an empirical question with real measurements behind it. And when the answer arrives, whatever it is, it will transform the precision with which we can assess habitability for every Earth-sized exoplanet currently in the catalogue and every one yet to be found. This is the deepest reason why Venus matters in 21st century science. It is not primarily about Venus. It is about the calibration problem at the core of the search for life elsewhere in the universe. We are building the next generation of space telescope successors to James Webb, instruments designed specifically to probe the atmospheres of rocky planets around nearby stars in the hope that they will one day detect chemical signatures of life in the atmosphere of an exoplanet. The targets for those telescopes will be chosen from the catalogue of potentially habitable Earth-sized worlds. But that catalogue is built on a definition of habitability that still carries the uncertainty that only Venus can resolve. If we do not know where the inner edge of the habitable zone truly falls, if we do not know what combination of atmospheric chemistry, geological activity, water inventory, and tectonic history determines whether an Earth-sized world maintains liquid water or undergoes a runaway greenhouse, then we do not know which worlds in the catalogue to trust. We may look at a planet labeled potentially habitable and point our best telescope at it for weeks, searching its spectrum for the signatures of water vapor and oxygen and methane, only to find we have been studying a Venus. Venus is telling us something that no other object in the solar system can tell us, with the same specificity, the same proximity, the same wealth of measurable detail. It is telling us what happens when an Earth-sized world in approximately the right place starts with approximately the right conditions and then tips over a threshold that its regulatory systems cannot counteract. It is demonstrating, in physical reality rather than in simulation, the exact chain of events: rising water vapor, UV photolysis, hydrodynamic hydrogen escape, HCO plus mediated ion escape, the failure of the carbon silicate thermostat, the irreversible accumulation of a suffocating greenhouse that converts a potentially habitable world into a permanently uninhabitable one. Every parameter of that chain is in principle measurable. Every measurement tightens the model. Every tightened model refines the habitable zone boundary. And every refined boundary changes the list of exoplanets worth examining for signs of life. There is a reckoning embedded in all of this that has nothing to do with Venus and everything to do with the planet you are standing on right now. Earth has survived not because the universe arranged circumstances for it to survive, not because there is anything special or protected about the third position from a sun. Earth has survived because a specific combination of physical systems has continued operating long enough in the right configuration to keep the surface of a rocky planet within the narrow band of temperature and chemistry where liquid water remains stable. Plate tectonics has continued cycling carbon through the crust and mantle, holding the carbon silicate thermostat in operation. Liquid water has remained on the surface to drive the weathering reaction that draws CO2 out of the atmosphere. The magnetic field generated by the convecting iron core has deflected enough of the solar wind to slow the atmospheric escape that, unchecked, would deplete the hydrogen reservoir, the water, over geological time. These systems are not permanent. They are contingent, operating within physical parameter ranges that will not last forever. The sun will continue brightening. In approximately 1 billion years, that brightening will push Earth toward the same threshold that Venus may have crossed 2 to 3 billion years ago. The outcome will eventually be the same. But 1 billion years is not now. The thermostat is running. The water cycle is turning. The plates are moving beneath your feet, and across every moment of geological time that these systems have remained operational, the conditions that allow something as improbable and as extraordinary as a biosphere to persist have continued to exist on this particular rock. What Venus has done in being what it is, in having the history it has, in being close enough for spacecraft to reach in a few months, and rich enough in geological and atmospheric data to occupy scientific careers for generations, is give humanity a precise instrument for measuring how rare that persistence truly is. Not rare in the vague sense that people sometimes invoke when they say the universe is a special place. Rare in the quantitative sense. How many planets of this size, at this distance, in this kind of star system, fail to maintain the regulatory loops that keep a biosphere possible? What fraction of potentially habitable worlds are Venus's? What fraction are Earth's? The answer to those questions, when they finally come in from the data returned by Da Vinci and Veritas and Envision, will be the most consequential numbers in the history of planetary science. We are the civilization that lives on the Earth outcome, looking across at the Venus outcome, 42 million kilometers away on its closest approach, and slowly building the instruments to understand what separated them. That understanding is not complete. It will not be complete for another decade at least, and possibly longer, but it is coming. And when it arrives, we will know something that no generation before us has been able to know with precision. Exactly what this planet is, exactly what it survived, and exactly how close the line between the two outcomes actually ran. Venus glows in the western sky after sunset, brighter than anything but the moon, and it has no idea what it is telling us. It is simply a planet running its physics, with its volcanoes erupting every few months and its acid clouds circling at 360 kilometers per hour, and its surface roasting at 465 degrees beneath 93 bars of carbon dioxide. Atmosphere, the locked and permanent result of a cascade that ran its course billions of years ago. The meaning we extract from it is ours, built from pioneer Venus mass spectrometers and Magellan radar, and the 2024 HCO Plus study, and 30 years of archived data waiting to be properly compared. The meaning is this: the line between paradise and hell is real. It is physical, it is measurable, and it ran right through the inner solar system, with one world on each side. We are the ones who landed on the lucky side, and we are, at last, learning exactly how lucky that was. Sleep soundly, dreamer, the morning star burns on, patient with all the questions we have not yet asked.